Biswajit, go ahead.
Thanks for giving me the opportunity to speak on our work. So I'll speak about, in general, trace anomalies, its connection to scattering amplitude in the case of renormalization group flow. So this talk will be based on few papers we wrote together with Denis, Jan, Joao, and Johar Komargowski. So one of the paper actually appeared today. Hopefully, if I get time at the end, I'll also talk about it. So, like in modern language, we kind of understand quantum field theory to be a renormalization group flow between two fixed points, like the UV and IR fixed points, and we consider they enjoys basically conformal symmetry. So this is kind of a rough picture of quantum field theory. It's basically nothing but a RG flow, and we start from UV CFT, and we can trigger the RG flow by kind of deforming the theory by some relevant operator, which is kind of which breaks the conformal symmetry explicitly, or we can give some vacuum expression value to any of the scalar primary operators of the CFT, and which basically does spontaneous symmetry breaking case. So this is kind of the setup which we want to think quantum field theory is. And now I will introduce or I will study this setup, introducing some set of background fields and how trace anomaly basically kind of constrain some action of the background fields in the low energy. So what we do is that we start with a UV conformal field theory, and let's consider it's a explicit symmetry breaking case. So we deform by a relevant deformation, and we couple the system by a set of background fields. And then along the RG flow, we integrate massive degrees of freedom, and we came to the IR fixed point, where it is described by IR CFT, which may also couple to the background fields, as well as since we integrated out some massive degrees of freedom, there will be a effective field theory in terms of the background fields. Now the questions we would like to ask is that, starting from this IR action, can we able to identify some observables which are associated only in terms of associated with the background fields, and can those observables are completely determined by the UV CFT and the IR CFT data, but won't depend on the details of the RG flow or how we deform the theory and all these details. And if we can identify such set of observables, and presumably if they are scattering amplitudes, possibly we can use the non-perturbative asymmetric bootstrap program, which Balt reviewed nicely, and try to put some constraint on the UV CFT data, which in general, like in case of CFT, there is a procedure like to do conformal bootstrap to put some bounds. But suppose there is UV CFT and we can trigger this to have a RG flow, then possibly using this background field method and the observables, if they depends only on the UV and IR CFT data, under some assumptions of the low energy, low lying spectrum of the QFT, hopefully we can able to also bound some UV CFT data. And this is the kind of questions we want to ask. Okay, and here, for the sake of simplicity, and I will only consider two sources, and the two sources are, one is basically some background like gravity, which is basically some non-dynamical cards, like we place the UV CFT in some non-dynamical card background, and we conformally couple the theory so that there is a Weyl invariance. And then after deformation, it breaks the Weyl symmetry. So to restore the Weyl symmetry, we introduce another field called omega, which is a compensator field, which basically compensates the explicit Weyl symmetry breaking, and this has some transformation property under Weyl transformation, where sigma is the infinitesimal Weyl transformation parameter. And to do that, you basically have to do that, you have to start with the QFT action and replace all the mass scale, basically you need to scale by this compensator field omega. And if you do that, then you basically classically restore the Weyl invariance of the theory, and you can integrate out the degrees of freedom and find a connected functional. So the only Weyl symmetry breaking of this theory at any energy scale should be only given by the trace anomaly coefficients, which are known to be these two terms, which is the okay, I'm assuming there are no other couplings or background fields, so there are only two terms which are given by AUV and the CUV, which are known as this A anomaly and the C anomaly coefficients, which appears as a coefficient of the Euler density, which is a particular combination of curvature tensor squares and Weyl tensor square is the CUV. So this is true, this has to be true at all energy scale, and this will refer to as the anomaly matching condition, because we can we can match this from the UV and the IR both places. So if we do that, then we can try to find out what will be the IR effective action, and this IR effective action, which basically the IR action which will contain the IRCFT action coupled to the background, like IRCFT action in placed in the curved background, and there could be some coupling to the IRCFT action with the dilaton graviton system and possibly IREFT. And this, like the hats are basically is a combined like metric, and they like all the scalar operators of the IRCFT, and those are kind of while constructed as a while invariant combination. And then one can solve for the anomaly matching condition and try to find what will be the effective field theory action, and one can find the effective field theory action, which are the coefficients of this delta A, which is given by this, like which is known as the West-Jumino action, and the delta C, and a part which could be invariant constructed out of the invariant metric, and there are few Wilson coefficients. So in the IR, the relevant path of the action contains the information about delta A, delta C, the some couplings of the IRCFT operators with the dilaton, which I am calling the lambda delta, and few Wilson coefficients. Now we can start with this IREFT action, or like the IR action, and try to compute various vertices involving this background fields, which I am calling the dilaton and the graviton, and we can compute various things and see how they depends on various Wilson various Wilson coefficients, as well as the change of the trace anomaly coefficients, which I am denoting by delta n and delta c, which are the difference of the UV CFT A anomaly and IR CFT, and similarly the UV CFT C anomaly and IR CFT C anomaly coefficients. Okay, so we can do that obviously, and we can see that this vertices depends on all the coefficients in most of the cases. So now we try to find that what could be the protected observables, which are completely determined by the say trace anomalies, which are the UV and IR CFT data, and independent of all the Wilson coefficients and the arbitrary coupling to the CFT and the dilaton fields. And to do that, we have to really consider some scattering amplitude involving these background fields, and for that we need to provide some dynamics to them. And giving this dynamics actually in our hand, we can do whatever we like, and the prescriptions what we use is that we don't want to break the general quantity invariance, and the while symmetry can be broken above scale f but not below that. So f is, I think I may forgot to mention, f is basically the parameter which we introduced to relate this omega to a new field phi, and at this moment you can think of f is just kind of a counting parameter, how many fields in observable, how many dilaton fields are there, and similarly kappa is a parameter which counts the number of graviton fields. So if we do that, then we have a system in the IR which will be given by the earlier action, but now we have some kinetic terms for the dilatons and gravitons, and try to see whether we can compute some amplitudes. And the first amplitude which has been computed by Komargowski and Swimmer from this action is basically the 4 dilaton amplitude, and what they have shown is that the 4 dilaton amplitude is completely independent of all the like theory dependent parameters, and it only depends on the change of the A anomaly coefficient, which I am denoting by delta A, and the STUs are the usual Mandelstam variables. And then they kind of studied the dispersion relation for this amplitude, and what they are able to show is that the change of the A anomaly coefficient from the UV to IR is always positive semi-definite, and this is known as the famous A theorem, that A monotonically decreases along the RG flow. We can try to identify whether there are some other amplitudes which can also be some kind of protected, and we found that if we compute the helicity flipping like graviton-dilaton to graviton-dilaton scattering amplitude, we saw that actually this is also completely determined by the UV and IR CFT data, and it is only given by the change of the C anomaly minus the change of the A anomaly coefficients, and it vanishes in the forward limit. So here we can also try to write down a dispersion relation, and the dispersion relation looks like this. Obviously this is not positive semi-definite, so obviously this coefficient does not flows monotonically from UV to IR, but from this dispersion relation we can, if we decompose into partial waves, we see that it only probes all the massive particles which we integrated out along the RG flow and which have the partial wave spin greater or equal to 2. So if it contains all the particles, then there is a possibility that the A anomaly delta A is which contains all the degrees of freedom which we integrated out along the RG flow, then it's positive semi-definite, but it is not. But this still is a universal change of the C and A anomaly coefficients, which could be useful from the asymmetric bootstrap setup to bound these objects. And also we know that for example, the zero partial spin zero massive state which we integrated out contributes similarly to both A and AC coefficients. Okay, now let me describe one at least bootstrap setup which we have done with these collaborators. So here we try to bound the A anomaly coefficient for a UV CFT which flows to a gapped QFT, and the low lying state or the mass gap of the theory will be given by a scalar particle which is G2 odd, which is just for simplicity. And for this kind of RG flow, the question we wanted to ask, what could be the, in the space of UV CFTs, what will be the minimum value of the AUV which can flow to a gapped QFT with the gap to be a G2 odd scalar particle. And for that, basically we need to study non-perturbatively basically three sets of amplitudes, like the scalar G2 odd scalars to G2 odd scalar particle, scalar dilaton and dilaton-dilaton amplitudes, and we parameterize this thing using this asymmetric bootstrap program Balt reviewed, but in the primal approach. Instead, I think he mostly focused on the dual approach. And if we do that, we found that the global minimum of the allowed A anomaly coefficients in the, basically this is the strength of the matter-matter scattering amplitude at some crossing symmetric point, and the minimal of the allowed region lies here, which is roughly the value like 0.32 times the free scalar A anomaly value, where the free scalar sits here. Okay, and this axis is the A anomaly the free scalar, the A anomaly value of the theory scaled with the free scalar value, and this is the allowed region. So it gives some bounds, though we don't know actually any example where the anomaly values lies, or any CFTs where the anomaly values lies below 1. Okay. So now with the time I have, let me try to explain one example how to work out this background field approach and whether it is useful to compute this change of A and C anomaly values, which is a simple example which we are calling weakly relevant flow. So what is a weakly relevant flow? We start with a UV CFT and with a deformation, and the deformation operator is weakly relevant in a sense, like the scaling dimension of it is 4 minus delta, where delta is much less than 1. And this lambda 0, which is the coupling of the deformation, is also we treat as a perturbative parameter. And in that, for this kind of a RG flow, actually there is it is a short flow, and there is a perturbative IR CFT. We can find a perturbative IR fixed point where the coupling value is given by this object, like proportional to small delta. And then for this model, we can work out the anomaly coefficients and how things changes. So, thank you. So the goal is basically we want to compute this change of the A and C anomaly values directly for the weakly relevant flow, possibly computing some partition function on sphere, some stress tensor correlators. On the other hand, we can couple the RG flow to the dilaton and graviton background, and then we can evaluate also various vertices follows from the the anomaly matching EFT action, and then we can compare and see whether this background field method is concrete, and whether maybe at some point it could be even simpler to use this background field method to compute the change of the anomaly coefficients. And also this agreement basically also try to relate these various vertices involving the background fields to the QFT correlators in a concrete way. So this is kind of the general prediction for the 3 dilaton vertex and the 2 graviton to 1 dilaton vertex from the the EFT I wrote earlier, the anomaly matching EFT. So you can see the 3 dilaton vertex contains only delta A and some Wilson coefficient R1, which appears as R hat square coefficient, and also graviton dilaton amplitude is a particular structure. So what you can do is that we can start with, now in our this weakly relevant flow, couple the way I explained to introduce the dilaton and place in a curved background, and then we integrate out the degrees of freedom along the RG flow and compute the EFT action. And the relevant part of the EFT action which contributes to these vertices are given by kind of these integrals with some QFT correlator like 2 scalar, like the 2 point functions of the deformation operator and the 3 point function of the stress tensor deformation operator. And we can compute these objects actually using conformal perturbation theory along with resum the leading logs using Callan-Simonjig equation, and we can find the particular expression for them, substitute, do this integral a bit mess, but finally we found the values of the delta n and delta c at leading order in small delta, and those agrees with some other computations from sphere partition function here for the delta n and delta c also independently compute from, because this c value is proportional to really the central charge in the CFT, so it can be read of also from the QFT 2 point function of stress tensor correlators. And I will leave, I think I don't have much time, so I'll leave with these take-home messages and end here. Thank you.
You have your bound on delta on A. Do you also have a lower bound on C?
So actually we don't have, but we can use this graviton-dilaton amplitude to do that. But what happens is that if we combine our this A value with the Malthus-Hoffman bounds where they have a over C ratio, we can also put a bounds on C. But that's not rigorous because there the A over C bound is for any generic CFTs. On the other hand, we are only focusing on the CFTs which can flow to gapped QFTs. So, but still combining this, we can predict, and we have a prediction for the lower value of CUV also. But it would be nice to study this graviton-dilaton amplitude and put a more stronger bound.
And also, I can also ask if it would change anything to include bound states like I had for the glue balls. If there's
Yeah.
that would change a lot your answer.
I think it will change even removing this G2 symmetry, like we consider only the G2 odd stable particle as the lowest. If we remove it, also this bounds really becomes, I think, instead of 0.32, it becomes like 1.18 times AUV. And if we also include more and more particles, possibly we can even push more towards 0. Obviously below 0 is not allowed from like the unitarity. We can even push the bounds much and more lowers.
But I would expect A to increase. So if I have a bound state in the theory, it's not just a simple massless scalar in the UV, right? Needs to be something more complicated.
Yeah.
So it goes the other way.
Yeah, maybe we will have more freedom to parameterize the amplitude, so we have more parameters to handle. So I don't know, maybe it could happen that it become weaker and weaker, the bound may become weaker and weaker.
Still nobody? We have a few more minutes. So what if you want to? What's the take-home message from your third paper? Because you seem to be doing a lot of conformal perturbation theory.
Right. So
have you learned anything that we did not already know?
Yeah.
Besides the quantitative results.
Yeah. So I think one thing we learned is that how to compute the change of the OP coefficients, because there we have to study the 3-point functions. And only conformal perturbation theory is not quite useful, because if you just go like, if you are close to UV fixed point, it's okay, but if you try to go far, it won't work. So you have to resum using Kalan-Szymanczyk equation. And this has not been done because there are many length variable in 3-point functions, like 3 and like 2 angles and 1 radial direction. But what we learned is that at least in 1D now we know that how to do that, and we can like get a 3-point function which is valid all points on the RG flow, like for at least for this example, and then we can compute the change of the OP coefficients for this from this 3-point function, which I think was not known. At least people only studied 2 point. Yeah.
How does it compare with the results we had 10 years ago? About the same.
Ours is D equals 3 though, this is D equals 4.
Yeah, I'm studying D equal to 4. Even we can do general D. So what is your result? I am not aware about maybe.
I think it's similar sort of conformal perturbation theory calculation. This was in D equals 3, so we can see these anomalies.
But do you also resum using Kalan-Szymanczyk equation?
Yeah, we did resumation, yeah.
Oh, maybe I am not aware about your paper. Maybe I should look at it. Okay. Thank you.
Right, if there are no more questions, then let's